Good afternoon, everybody. Today we have the great pleasure to have here at the seminar Manuel Sandoval Vallarta, a great expert from the University of Valencia, José Valle. He's an expert on particle physics, elementary particle physics, in particular neutrino physics, astroparticles, cosmology. He has made important contributions to this particular area, even cited by the Nobel Committee. But let me tell you more about him. He finished his PhD in '82 at the University of Syracuse, New York, and then he moved to do a postdoc at the Rutherford Appleton Laboratory in the UK, and working with several people, among them Graham Ross, who was recently, unfortunately, deceased in Oxford. And then he moved as a visitor professor at the Universidad Autónoma de Barcelona, and then at the University of Valencia between '87 and '90. He was already well known by his contributions, and then he was appointed as investigador científico at the Consejo Superior de Investigaciones Científicas in Spain. And then he also because of these contributions that he made, he received a series of prizes, for example, the Humboldt Research Award, the Medalla de la Sociedad Mexicana de Física here in Mexico, as well another prize in 2019, the Premio México de Ciencia y Tecnología. He has written around 400 different papers with great contributions. He has a lot of citations. I guess I read something like 40,000 citations. He appears as one of the most cited persons in many journals in different years. So his contributions to the particular field of neutrino physics has actually opened a new area of research, and I guess we all are going to learn a lot from him. Thank you, José Valle, for being here. It is a great honor. Please tell us about what is next in particle physics.
Okay, thank you very much for the generous introduction. Thank you for the invitation, first of all. For me, it is always a pleasure to be in Mexico, even if virtually. I have many friends in the Mexican physics community, and my task here is going to be to describe how neutrino physics, the discovery of neutrino oscillations in particular, has opened a new era in particle physics, and how neutrinos can help us forecast what will come next in particle physics. In other words, many of the shortcomings of the current theory of particle physics neutrinos may open many hints towards the solution of these shortcomings. So let me start from the discovery of neutrino oscillations. You see here, in my pointer, I'm pointing here, out of the nature of sources of neutrinos, solar neutrinos produced in nuclear fusion reaction in the interior of the sun, and atmospheric neutrinos produced by cosmic ray interactions in the upper atmosphere, they have brought us the discovery of neutrino oscillations, which led to the Nobel Prize in 2015. Here I show the associated parameters. On the left, you see the solar neutrino oscillation parameters, the 1-2 sector. You see here the square mass splitting plotted versus the corresponding mixing angle. You see how the splitting determination is driven by the reactor experiment 𝗙𝗲𝗰𝗵, while the solar data gives us somewhat better measurement of the mixing. Going to the atmospheric sector, you see the same information, the corresponding information for the atmospheric sector. And in particular, you see the important role of the deep core setup in the ice cube neutrino telescope located in the South Pole. This is an under ice experiment 2 kilometers below the polarized, and it is helping in a very important way in the study of atmospheric neutrino, which was pioneered, of course, by the Super K experiment. So one has basically that the study of solar and atmospheric neutrinos has given us the discovery of the oscillation phenomenon. But following that, reactor and accelerator-based experiments, the reactor is here, Reno and 𝗙𝗲𝗃, and accelerator, you have first T2K in Japan, then, sorry, K2K, then T2K also in Japan, that is a current experiment, and NOVA in the United States, and MINUS, they are not only confirming the oscillation phenomenon, but improving parameter determination in a substantial way. In particular, the very recent conference in Korea, the Neutrino 2022 conference, brought us a precision measurement using the last piece of data from the 𝗙𝗲𝗃 experiment, which was already the most constraining one for 𝗙𝗲𝗀. Now we have a real precision measurement of this parameter better than 3%. So this is this really is a revolution in particle physics. We have started doing precision physics in the lepton sector, analogous to the physics that we used to do, and we still do, of course, within the 𝗙𝗂𝗃𝗁 or quark sector. Now I come to a little bit of a drone view of the oscillation chi-square maps. These are, here is the chi-square, how the minimization leads to a determination of the solar mixing, a determination of the atmospheric mixing, determination of the reactor angle, and also the solar mass splitting, the atmospheric mass splitting, and the leptonic CP phase that enters in the oscillation, the so-called Dirac phase. You see here that everything is very, very neat, and these are very good determination, except for three things. First, the ordering of the neutrino masses. You see here in this upper part, there are two possibilities: the normal ordering, in which the electron type neutrino lies mainly in the lowest lying mass states, and the inverted ordering, where the 𝝻𝜺 appears in the upper, in the heaviest states. One is called normal ordering, the other is called inverted ordering, and you see here they both give acceptable solutions. The preferred solution is with normal ordering, but the other one is not ruled out. It is also accepted, and so we need to improve the situation there. Then you have the issue of the octant of the atmospheric mixing that I show here. First of all, the atmospheric mixing is nearly maximum, and this comes as a surprise. There is nothing in the quark sector of this type. You see also that the solar mixing is about 30 degrees or higher. Again, there is nothing about that in the quark sector. So the determination is good, but the atmospheric octant you see here, for each ordering choice, you have a preferred solution in the higher octant, but you have a secondary minimum in the lower octant. So the situation is still not completely stable. And finally, and partly as a consequence of this ordering ambiguity, we have a very poor determination of CP violation, the associated Dirac phase, for the case of normal ordering. You see in blue, this is not a very good determination. That would be the determination for inverted ordering. It's somewhat better, but inverted ordering itself is not favored. So we need to improve upon these three measurements. I should say here that if there are model builders in the audience, that the chi-square maps of our global field, which is published in JHEP. I should say there are two other groups doing this kind of thing as well. One of them led by my first PhD student. She's now a competitor in this field. It has a very good group. And also there is an Italian group. But I am presenting here our results. So our chi-square maps are all downloadable from our global feed, from our website. And also we go further than just giving the individual determination of each of the oscillation parameters. We present all of the correlation plots involving every single pair of the oscillation parameters. So that's very useful for model builders to test a given model of flavor. Now, the reason for this problem, for the poor CP determination, partly comes from the fact that there is a clash. There is between this experiment here in black, which published its results in Nature. This is the 𝗤𝗏 experiment, and the NOVA experiment in the US. The 𝗤𝗏 has a baseline of about 300 kilometers, while NOVA has a baseline of about 800 kilometers. And of course, matter effects should be included in doing these studies, because the Earth, matter effects in this case, within the Earth. So this is a problem that we need to sort out in the future. And there are, of course, experiments planned to do that. One is the deep underground neutrino experiment, dubbed DUNE, and located in the US using neutrinos made in Fermilab and detecting them in the underground facility where Ray Davis pioneered the field of neutrino physics, solar neutrino physics, in the 60s. These will study and sort out the issue of CP violation, and also an experiment in Japan, the hyper version of super K, which is currently already funded and in construction. So this is physics for the next 10 years. If you take the three neutrino paradigm I just described before, you expect a sensitivity for the determination of CP violation in DUNE, indicated by these black lines. So you see that near 90 degrees or minus 90 degrees, you expect a sensitivity higher than 5 sigma. And this may not be the very latest simulation, by the way, but it gives a pretty good idea. And the point I want to make is that in theories of neutrino mass, there is a broad class of theories, so-called type 1 seesaw models, which, if they are realized at low scale, they give the neutrino mass through the exchange of some heavy mediator, heavy lepton. And in this case, there are other phases that appear and which can get confused with the delta CP of the previous plot. So because of this possible confusion or this intrinsic degeneracy, one degrades a little bit the good determination that one can make in the standard paradigm. However, the degradation is not that bad. It is characterized by this parameter alpha to 1 and others, but this is the most important one, which characterizes unitarity violation in the leptomic simetries, something that we proposed already in the 80s and which is now coming back. The point here is that you need, if you know that you are in the unitary regime, you have a better determination. So the better the bound, the closer you are to the three neutrino paradigm. So to have a robust determination of CP, you need to have a good bound on alpha to 1 and other unitarity violating parameters. The relevant papers are indicated here if you care to go to the original references. There are many more. So that is one thing. The determination of the good determination of unitarity is required for a robust CP determination program in the future at Dune or similarly at 𝗥𝗲𝗀𝗂𝗁𝗂. But the determination of limits on alpha to 1 is an object of interest on its own right, to the extent that it will shed light on the origin of neutrino mass and what is the associated scale of the mediating particle. So much for the Dune experiment. There are similar studies for 𝗥𝗲𝗀𝗂𝗁𝗂, but I will mention now a European proposal, the European spallation source neutrino superbeam experiment also provides, again, this determination. In fact, for some parameter choices, somewhat better, although the experiment is still a proposal. Everything is changing for the moment, but there is a potential there to have a third competitor in this. Finally, the other point that was a missing link, we had the CP, the ordering, there was the octant. The octant will also keep us busy for a while. It will provide an important challenge for experiments. So much for the determination of CP, of neutrino oscillation parameter from experiment. Now I turn to theoretical interpretation. In the absence of a theory of neutrino mass from first principles, which I will discuss later, some possibilities, people tried just to do some numerology, and our British colleagues 20 years ago, they coined what is now called the 𝗙𝗲𝗰𝗵 pattern, neutrino mixing pattern, which became extremely popular and influential in the field because, first of all, of its simplicity and the fact that it captures the most essential features of the oscillation. You have here bimaximal atmospheric mixing, and you have a trimaximal solar mixing, has the name 𝗙𝗲𝗰𝗵. Moreover, you have zero reactor mixing, and as a consequence, no CP violation in the lepton sector. Of course, this is no longer viable, this pattern. It is ruled out. Yet, it still serves as a starting point from where we can obtain generalizations which are not only viable, but also predictive. I will show one example. The procedure is very systematic because it just exploits symmetries. And there is a whole bunch of papers trying to do this, to present these generalizations. Here I show only one example, actually two. This first one gives these green predictions, two relations among analytical relations amongst the oscillation parameters, which gets mapped into this plane of delta CP versus sine squared theta to 3. I call this plane the ignorance plane because it involves the two of the oscillation parameters that are worst determined. So the prediction from the generalized TBM in green is this green band, and you see that it overlaps the generic regions obtained by the global oscillation fit with just 3 neutrino within a restricted value of, for example, letter CP, indicating the degree of predictivity. There is another brother of this same, which is the black line, which is not so good. And likewise, there are many more possibilities. So TBM is not a viable pattern, but it is still a good starting point. There is another pattern that we suggested in Valencia, which exploits the observation that the largest quark mixing, the 𝗥𝗲𝗀𝗂𝗁𝗂, is similar in magnitude to the smallest of the leptomixing angles, namely the reactor. So, in this kind of scenario, one writes the leptomixing matrix as a product of two factors, one coming from the charged sector, the other coming from the neutral sector, both of which are expanded in a power series in lambda. Okay? So, in fact, the 𝗙𝗲𝗰𝗵 angle may be regarded as the universal seed for Fellman mixing. Okay? So, if you know lambda, you know the mole, and this is exactly what you can see here in this plot. It shows the solar angle in black, and you can see that the good measurement of the reactor angle gets escalated into a good measurement of the solar mixing. And also, the same feature also happens for the atmospheric. In this limit, we don't have CP violation. Well, we actually have, but we did not plot. It is up there. Okay, this is a very predictive realization of a bi-large mixing hypothesis. There is a less tight one, which is analyzed in this paper. I will not bother you with details. And there are many other possibilities. For example, tri-maximum mixing, TM1, TM2, golden ratio, etc., etc. Many of these ansatz can be probed in the upcoming 𝗙𝗯𝗀𝗰𝗵 setup, and of course, the hyper-K setup. This paper analyzes the potential of 𝗙𝗯 to probe different mixing patterns. Now I turn to neutrino-less double beta decay, because if you notice, neutrino oscillation is sensitive to the mass splittings between neutrinos. Only two mass square splittings. But there are three masses, so they don't tell about the absolute mass of the neutrino. The neutrino-less double beta decay experiment involves all three neutrino mass parameters you see here, weighted by the corresponding element of the leptomixing matrix. And here I should say that the best way to express the leptomixing matrix is not what is prescribed by the PDG. The PDG basically provides a parametrization which is of our type, but they put the Majorana phases in the wrong place. Of course, you can do that, but you have to be very careful because it introduces ambiguities and it is not at all theoretically, how can I say, transparent. It is confusing. But of course you can do. I'm not saying the PDG is wrong. I'm just saying that the best parametrization of the leptomixing matrix for describing neutrino-less double beta decay is one in which each CP phase and only the two CP phases that are of Majorana type can appear here. These are the CP phases that do not appear in oscillation, and their origin was explained in the old paper, why they are there and how many are there for different mixing possibilities. You have to go there to understand. So you see here, you have 1, 2, 3 mass parameters involved, and you have only 2 Majorana phases, and you don't have the Dirac phase. If you use the PDG form, you find the Dirac phase in your answer, and that is nonsense. You have to filter it out. That introduces ambiguities and so on. But of course, if you know what you're doing, of course, that can be done. The advantage of the PDG is that to describe oscillation, it becomes pretty obvious that the Majorana phases do not come in. But we know that. We don't need to write the way they do to know that. That's anyways. So this parameter in beta beta is a measure, in some sense, of the absolute scale of neutrino mass. And typically, if you look in any publication, it is plotted versus the lightest neutrino mass parameter. And this is, it makes sense it is perfectly okay. However, noticing that the most favored possibility for having a large rate for neutrinoless double beta decay happens when the neutrinos are nearly degenerate, I present here an alternative way to plot this m beta beta parameter instead of versus the lightest neutrino mass versus this degeneracy parameter eta. So when eta is 1, neutrinos are exactly degenerate, and this is the black line up there. And of course, in this case, you have a very big rate for neutrinoless double beta decay, already ruled out by the brown band, which is the experimental one that comes from the 𝗙𝗯𝘀𝘁𝗂𝗃 experiment. Of course, in real life, you cannot be in the strictly degenerate limit because you need to generate neutrino oscillations, so you must deviate a bit from that limit. There are two ways to do it. Either you go to the left within this normal ordering branch, or you go to the right in this inverted ordering branch. This is okay. You see that for the normal ordering case, you can have a cancellation or a destructive interference amongst the three neutrinos whose exchange induces the process, while in the inverted ordering branch, no cancellation is possible. All these are well-known facts. I'm just presenting them differently because it's kind of cute, and it lets you appreciate better the power of cosmology. The cosmology, well, I guess you can also do this in the other description. Anyways, cosmology provides this vertical excluded band that you can see here, which is in fact relatively wide, showing that it provides a bit more restrictive power than the neutrinoless double beta decay experiment itself. It comes from the studies of the CMB and the relevant paper. I call it a pandemic paper because it was a 2020 paper, which showed that this vertical band is excluded by the cosmological limit. You can do exactly the same in the standard parametrization, but this one is kind of cute. Okay, so much for this quasi-degenerate neutrino possibility. The conclusion is quasi-degeneracy is strongly disfavored cosmologically, but of course, I don't mean to imply that since cosmology gives you more restriction, that the neutrinoless double beta decay are irrelevant. By all means, they are crucial experiments, they are complementary, and they must proceed. In fact, I'm just coming from a conference just dedicated to neutrinoless double beta decay. This is an extremely important experiment, also because, as I will comment later, it is sensitive to the Majorana nature of neutrinos, which is an extremely important experimental goal. Okay, too much for quasi-degeneracy. The next best bet concerning having a large rate for neutrinoless double beta decay happens when one neutrino is massless or nearly so. In this case, these two bands, blue and orange, correspond to the two bands up there, blue and orange. And you can see something new. In the blue case, there is an absolute lower bound on the neutrinoless double beta decay amplitude, which is generically absent, indicating that no cancellation is possible in this case. On the other hand, if you go to the inverted ordering situation, you see that the corresponding band here is much thinner. This observation is really not very deep. This is a very trivial. I mean, everybody can make this plot. In fact, there are many, but somehow it was not pointed out until 3 years ago, that this is the feature of the one massless neutrino scenario. And as I will describe, one massless neutrino scenario can be theoretically motivated. So it's kind of interesting to point out this possibility. Here, the current bands, the current limits are indicated by these colored bands. They are not lines, but bands, and the width of the band indicates in each case, the uncertainty from the nuclear physics calculation. And concerning the future lies in these black dashed lines. And this is extremely interesting that this scenario will be fully covered by the next round of experiment. As you can see here, the Nexo experiment in the United States fully covers the expectation for this scenario if the ordering is inverted. If the ordering is not inverted, you lie below. What would happen if, though, all three neutrinos were massive? Then we go back to the standard situation, and I now present the m beta beta, like everybody does, namely versus the lightest neutrino mass. And you can see here, this is the standard, this shape for normal ordering is the standard prediction for that case. And you see this colored line that corresponds to the prediction of a particular family symmetry-based theory. So the message here is that even though generically there can be a cancellation for normal ordering, this cancellation happens to be forbidden in many theories which attempt at explaining the structure of the mixing angle observed in neutrino oscillation. More often than not, they lead to a lower bound. There are many more references that I have not put here in order not to clutter the slide. And I choose to plot a particular recent one from this 𝗔𝗯𝘀𝘂𝗺 paper. In fact, there are two examples. In both cases, you see that the preferred, for example, here, the preferred element, the preferred value lies exactly in the range which is cosmologically interesting. Okay? So all these are different models. In other words, you can appreciate the legacy of the oscillation experiment. Oscillation is telling us also something about neutrino 𝗙𝗲𝗰𝗵 decay, not directly. It is not a very, very tight thing, because oscillation can happen, for example, with Dirac neutrinos. And neutrino 𝗙𝗲𝗰𝗵 decay only happens for Majorana neutrinos. In fact, this connection would be a very deep connection, namely, if you ever discover neutrino 𝗙𝗲𝗰𝗵 decay, and you know that the associated amplitude is non-zero, that amplitude can always be dressed by the exchange of the W boson, so as to produce a Majorana entry for your neutrino mass matrix. And in that case, at least one of the mass eigenstate neutrinos will be a Majorana particle. So this is a deep result, which is just becoming 40 years old. It comes from 1982, and it is still there. If you discover neutrino 𝗙𝗲𝗰𝗵 decay, we will know that lepton number is violated in nature. There have been many subsequent papers. The middle one is a theory paper that tries to make the argument quantitative, and the lower one is an experimental paper, which I advise if there are students that want to learn, because it is of the 𝗙𝗲𝗃 school in the United States a couple of years ago. Okay, so much for experiment. Now I move to theory. What is the origin of the neutrino mass is perhaps the most well-kept secret of nature. And I show here the picture of Majorana because out of all the fermions of the standard model, neutrinos are the ones that we know are massive, and most likely their mass is a Majorana mass, differently from all of the other fermions, which cannot be so because they are electrically charged, and so they must be Dirac fermions. Weinberg also went further in this direction, arguing that even though the standard model lacks neutrino mass, the doublets present in the standard model, the Higgs doublet responsible for symmetry breaking, and the lepton doublet, allow you to construct a unique non-renormalizable dimension 5 operator, which turns into a Majorana mass below the symmetry breaking scale. This is, however, very far from a theory of neutrino mass. To go any further, one needs to do what we theorists call a completion of Weinberg's argument, and the seesaw provides a completion that I find attractive because it opens the possibility of dynamically explaining the small neutrino mass by minimizing the Mexican head generalized Higgs potential, responsible for Majorana neutrino masses. So this is a deep connection. You can have a dynamical understanding of the small neutrino mass by minimizing the a generalized Mexican head. And in such a generalized Mexican head, you have another very interesting possibility, namely understanding the stability of the electroweak vacuum. The electroweak vacuum stability is not at all guaranteed in the standard model, but it can easily emerge from the seesaw mechanism, as demonstrated in these various papers for different possibilities. Within a seesaw scenario, neutrinos will acquire mass either by exchanging a heavy right-handed neutrino, today is called type 1, or by exchanging a heavy triplet scalar boson, today called type 2. In our original seesaw papers in cyan color, we named these things just the opposite. Why did we do so? First of all, the terminology did not exist. We could have invented it, and we would have called it differently. The reason for that is that the triplet seesaw is the simplest seesaw. Period. This is the simplest seesaw. But this today sounds like an anecdote, and there was more than that. The difference between the yellow seesaw and the cyan seesaw is that the cyan is more general, because that was a standard model-based seesaw, while the yellow seesaw all assume left-right symmetry of one type or another. And that implies, by gauge symmetry, that you must match the number of right neutrinos to the number of left neutrinos. In a standard model-based seesaw, you don't need to do that, because right neutrinos are gauge singlets. You can add any number of them. In particular, you can have what is now called a missing partner seesaw, in which you add less singlet neutrino than doublet active neutrino. For example, you have 3,2, or you can have 3,1. 3,2 is the minimum viable type 1 seesaw right now. And 3,1, in that case, both mass scale come from the seesaw, both the atmospheric splitting and the solar splitting. And one of the neutrinos is massless, leading to the minimum value of double beta decay that I just described previously. There is a lower bound for double beta decay. You don't have this possibility in a standard left-right symmetric seesaw. The other possibility, I think it's even more interesting. You can have 3,1, and that means that only the atmospheric scale comes from the seesaw. This explains why the solar scale is smaller, and the reason is that it comes from radiative correction. And the model of this type, which is very simple, it was dubbed a Scotto seesaw, because it puts together the seesaw paradigm for neutrino mass generation with the weak interacting massive particle or WIMP paradigm for dark matter. They put them together. So the template for this is the 3,1 in the Schechter classification, the 3,1 type 1 seesaw. Okay? And that leads to the lower bound on the beta beta that I described. Both models give exactly the same lower bound I described before. But you can also go in an opposite direction. You can have more singlet neutrino than doublet neutrino or active neutrino. And a very simple one is 3,6. So you have the 3 active neutrino, and to each active neutrino, you add a pair of singlet neutrino. And in the symmetry limit where lepton flavor is conserved, those will be Dirac famous. So there will be 3 Dirac neutrinos added sequentially, okay? And the 3 active neutrino will be massless as the neutrinos of the standard model. So there is a common template for this model, but the neutrinos are massive. Okay? But that situation constitutes the template to provide models of with light neutrino masses, which today they go under 2 different names, the inverse seesaw, and the other class is linear seesaw. They share the same template, but they are different seesaw. In fact, one is called linear because of the different way the neutrino mass appears in those models. They are not quadratic in the Dirac-ภิokawara coupling. They are linear. Here I will indicate the inverse seesaw, which is kind of simpler to understand. And what we do to generate neutrino mass in this model is to add a small seed of neutrino mass in the hidden sector, in the singlet sector of neutrino. Okay? So if that seed is small, neutrinos are light. Neutrinos become massless as that seed go to 0. And this is totally natural from a symmetry point of view. It means that the small neutrino mass is symmetry protected, but it is protected not in the sense of Weinberg, but in the sense of 't Hooft. Our famous 't Hooft of QCD. He argued that in a Lagrangian, you can put to 0 all the couplings which are such that in their absence, the theory acquires a higher symmetry, in this case, lepton number conservation. So, in fact, the lepton number protection provided by the inverse seesaw can actually be a double protection if you can arrange that this blob, instead of being just a number that you put in your Lagrangian, is a calculable quantity associated to yet another layer of physics, for example, here on the left or here on the right. And I will call your attention to the right possibility, which we dub the dark inverse seesaw, where the seed for neutrino mass generation is the dark matter sector, which is a hidden sector. Okay? Dark matter in this case is a weakly interacting massive particle, WIMP dark matter, that can give the right relic density. I plot here on the left, omega A squared, H squared, for typical TeV values of the mass, and it could be a scalar WIMP dark matter. So this is a pretty decent model of dark matter, which can give rise to the right relic density, which I show here for different benchmarks. And these can be probed in the so-called nuclear recoil experiment, the most sensitive of which at the moment is xenon 1 ton. And their result here is showed in this curve, the sensitivity of WIMP dark matter for this benchmark, and you can see the model prediction. So this is a nice dark matter model, but remember, it is a neutrino mass model, So there is a whole plethora of new physics associated to the inverse seesaw, which I show here, for example, the example of 𝗔𝗯𝘀𝗂𝗵𝗵 and other 𝗔𝗯𝘀𝘂𝗵𝗵 violation processes, which may proceed with rates that can be accessible to experiment. But this low-scale seesaw also lead to the possibility of being probed at collider energies, such as the Large Hadron Collider at CERN, or its successor, which is currently planned, the Future Circular Collider and other colliders, 𝗙𝗏𝗏 colliders that are now planned, for example, the ILC and others. The idea is very, very simple. I will show this idea for the case of type 2, because it is pretty neat in this case, because I mentioned to you type 2, which actually should be called type 1, is the simplest seesaw. And in this case, you can produce the mediators of neutrino mass generation and study their decay properties. So in the triplet seesaw, you have this doubly charged guy, which decays to a pair of muons. So you can have a 4-muon signature, for example, in 𝗙𝗏𝗏 collision or proton-proton collision. And here is the cross-section for a 3 TeV lepton collider. And you can see how the cross-section depends on the lightest neutrino mass. You remember the neutrinoless double decay observable there. I plotted them beta-beta versus there, but then beta-beta was a tiny thing, sub-electron volt. Here, this is a cross-section that you can measure at an experiment with the center of mass of 3 tera-electron volt. And you can have a 4-lepton signal that depends on the lightest neutrino mass. Here you can see the scattering limit obtained by measuring, by probing the neutrino mass in tritium beta decay, the Curie probe of tritium beta decay. And you can see the sensitivity of cosmological CMB studies. You can see that it goes better than that. And you also see something spectacular here, namely this experiment is sensitive to whether the neutrino mass ordering is normal or inverted. You can even go further. You can go to a 4-lepton signal in which one of the final stage lepton has a different flavor. Here you see 3 muon and an electron flavor. So this is a lepton, charged lepton flavor violating observable of the same type as 𝗔𝗏𝗏 at low energies. So I plotted this cross section for the same parameter as the left plot, but I displayed it with respect to the branching ratio for 𝗔𝗏𝗏, which is currently, there is a band which is ruled out by the MEG experiment, indicated here in color. So you see all the parameter space to the left of this band is okay with 𝗔𝗏𝗏, gives 𝗔𝗏𝗏 at 10 to the minus 20, 15, 10 to the minus 20, 25, or even 30. Yet the corresponding cross section at high energy could be as large as indicated by these curves here on these plateaus. This indicates what? Indicates that high energy collision can be the discovery site for charged lepton flavor violation. Or said differently, charged lepton flavor violation can be discovered at this experiment rather than 𝗔𝗏𝗏 or 𝗵 to E conversion in nuclei. So much for Majorana seesaw. Now you see that I changed the photograph of the slide. Now it is the photograph of Dirac. To say that you can seesaw a la Dirac. You don't need to have Majorana neutrino to implement the seesaw mechanism. And there has been in the past 6 years a whole bunch of papers in the literature trying to produce Dirac seesaw mechanism, either from first principle or just from general operator classification. And you can have type 1 Dirac seesaw, where the seesaw is mediated by a Dirac-lepton exchange, or type 2 Dirac seesaw mediated by a scalar now coming from a doublet scalar, typical two doublet scalar model instead of triplet seesaw. The models are a little bit more complicated than the Majorana seesaw, but the idea is exactly the same. The main thing is you need symmetry, both to protect the small neutrino mass and symmetry to protect the Diracness of the neutrino. In some theories, the symmetry to protect the Diracness is nothing but the 𝗥𝗀𝗀𝗁𝗁 symmetry that people appeal to in order to explain the small dipole moment of the neutron. There is another possibility, namely the Diracness could arise from the symmetry associated with dark matter stability. So this is interesting connection. These theories are also interesting, even though they are less popular in the literature. Now I turn here to another drawback of the standard model, namely the flavor problem. Why there are three flavors of elementary fermions in the standard model, and why they appear with the parameters observed in nature. The standard model lacks an organizing principle in terms of which, to understand the flavor problem, we need to go beyond the standard model, and it is here somehow neutrinos offer an important legacy. Neutrinos have taught us a lot. They have taught us, first of all, that lepton mix. The lepton mixing here is indicated in blue. The quark mixing is indicated in red. So oscillation have left a legacy that leptons mix, but also that they do so rather differently from the way quark mix. You see here a feature I mentioned before. The smallest of the lepton mixing in this small circle is similar in magnitude to the largest of the lepton mixing, and we have no understanding of this whatsoever. Okay? So this is one side of the flavor coin. It's like a coin. One side is to understand this. The other side of the coin is the mass quark-lepton mass hierarchies. I already mentioned that this is the scale of the fermion masses from milli-electron volt all the way to tera-electron volts. I already mentioned the seesaw as a way of understanding why neutrinos are so peculiar, but this does not exhaust the flavor problem. The flavor problem lies here in the charged fermion mass. Nobody understands why the top is so special, or why the muon is 200 times heavier than the electron. I don't have an explanation to this. Nobody has it. But I can say one thing to appreciate the legacy of the oscillation, namely, in trying to make sense of the mixing pattern between quarks and leptons, people have derived a whole bunch of ultraviolet complete or theories from first principle, in which all of which converge into a unique formula explaining the masses of the tau lepton and of the bottom quark. You see here, all these references are different family symmetry theories, and there are more. Only some are shown here. But all these different theories neither can be claimed yet to be the final theory. They all converge into a unique prediction that I call golden quark lepton mass relation, which is extremely good, and which involves the tau lepton with the bottom quark mass and involve all the three families of fundamental quarks and leptons. So we don't have a complete theory, but we have a very attractive formula, which is definitely not complete. It does not explain the mass of the top quark, but perhaps it contains part of the ultimate answer to the flavor problem. But I admit the flavor problem is so profound that perhaps we should be more ambitious in trying to obtain its possible solutions. Maybe we can go beyond the domain of four-dimensional gauge field theory to theories involving extra space-time dimension. And there is a proposition which is called warped flavor dynamics. The idea here, if we imagine that you have 5 dimensions and the 5th dimension is curled up. And this curled up dimension, its presence, may perhaps explain the pattern of fermion mass hierarchies as resulting from the geometry, the Kārl geometry of the extra dimension. I show here some references, especially 𝗥𝗲𝗀𝘁𝗂𝗺 went in this direction. And we tried, but this does not exhaust. First of all, it's kind of a funny solution because you say the flavor solution comes from geometry, but now you need to be a mathematician to know the geometry, the right geometry that reproduces the masses of all the standard model flavors. Moreover, you need to explain also their mixing. And we suggested in Valencia that maybe the mixing can be obtained as we do in four-dimensional field theory. The explanation for the mixing may come from the imposition of a non-abelian family symmetry. For example, T prime is a small family group, very simply related to A4. It is the covering group of A4. It is the smallest group that has three-dimensional irreducible representation that you can use to stack the three families of fermions into a triplet. And it provides this M1 prediction shown here, two very simple analytical predictions for the mixing coefficient of the mixing parameter of the oscillation experiments. So this is very nice because the TM1 pattern, by the way, already existed before as a phenomenological pattern. It is, here we have a derivation of TM1 from first principle and a very successful pattern. You can see here, this is our ignorance plane again. In green, the most fully determined of the oscillation parameter. And you can see here a very tight prediction between the modulus of CP phase and the atmospheric mixing. And in vertical here, you have the determination of the atmospheric angle, the preferred octant determinations. They lie in the upper octant, both for normal as well as for inverted ordering. So there is a continuity between oscillation physics and what you can predict here. Neutrino 𝗙𝗲𝗀𝗁𝗍 is another prediction. You can see here the amplitude for neutrino 𝗙𝗲𝗀𝗁𝗍 and beta beta plotted versus the lightest neutrino mass parameter, as everybody does. And you can see here in green the prediction, the generic prediction for three neutrino paradigm. And you can see the prediction of this model in blue, totally covered by the next round of experiment, in particular, the Nexo experiment. And for the case of inverted ordering, you can have even higher. The ordering itself is not predicted. Another possibility along the same warp flavor dynamics proposition, you have the possibility of deriving TM2 from first principle in another realization of word flavor dynamics. These are 5-dimensional word models. You may go to 6-dimensional construction, and here I go to the case which is called orbifold, where the extra dimension are basically a flat space, except for some singular points where the curvature is infinite. Mathematicians call this construction, there are particular cases of 𝗙𝗲𝗀𝗂𝗁 called orbifold, and they can be compactified on tori. And what is nice about this scenario, you can see the details in this paper, is that you can derive the 4-dimensional family symmetry as a unique emergent symmetry. And that symmetry is a 4, the smallest symmetry that you can use to stack the 3 families in a triplet. And you see the emergence of the 𝗙𝗀𝗀𝗂𝗺𝗂𝗁 mass relation as a consequence of this theory that I show here numerically, its implication for the Down and Strange quark mass. They also provide prediction for neutrino oscillation. This is the prediction for the CP phase. The sign of the CP phase is predicted. Normally it is not. In our previous model, only the modulus was predicted. Here the sign is predicted, and in some realization, we have a very tight prediction also for the value of that phase, and this leads to prediction for oscillation. For neutrinoless double beta decay, you see here, we don't cover, we are not covered by the next round of double beta experiment. It does not cover, for example, this possibility here, but at least we can cover part of the chunk of predicted neutrino oscillation. I should say we also have a complete global fit of the flavor observables, and we can also incorporate the dark matter. And I must also say this paper, both papers are with Mexican collaborators, 𝗙𝗀𝗀𝗀𝗁 and 𝗙𝗲𝗀𝗂𝗁𝗁, which is in Guanajuato. Okay, with this, I come to our conclusion, namely that the neutrino oscillation discovery that led to the Nobel Prize in 2015 changed the panorama in particle physics, opened up a new era, and a vibrant oscillation program, which include not only neutrino oscillation experiments, but also searches for neutrinoless double beta decay. And from the experimental side, I indicated 2 other type of experiments which are extremely important: searches for charge lepton flavor violation, both in U2E gamma and UE conversion, as well as in the domain that I suggested of high energy collider experiment at the Large Hadron Collider or the 𝗥𝗍𝗁. Okay. In overall, there is a whole bunch of new theoretical insights that one can gain from all these neutrino oscillation experiments. So this brings me to my conclusion. Thank you very much for your attention.
Thank you very much. From here, I guess we can give a clap, a Zoom clap with the end. Thank you very much for this very interesting talk. I guess there are some questions in the audience, please. Anybody? Well, I have a question regarding the flavor puzzle, let us call it like that. Basically, the issues that you were mentioning are being there, particularly in the flavor sector, since, I don't know, many years, say 20, 30, 40 years. And people came out with this idea of the symmetries. There is progress in these symmetries. But is there any other choice in order to address this problem? Because it seems that everybody has his favorite flavor symmetry, and everybody can actually predict different features from the neutrino sector, but there is kind of the difficulty to discern, to distinguish among the different models, right? So is there another choice?
Well, I am fond of symmetries, but I completely agree with you. As you see here, these are some examples of papers using different symmetries to try to understand this mess. Okay? And of course, it is a artisanal procedure. If you want to derive a theory, a UV complete theory from first principles, you are at a loss because you don't know the symmetry. So you have to, but it is well defined. There are some rules of the game, and it is, I think, a viable method of proceeding. And in particular, I exemplified, in this case, common denominators that can appear out of different propositions. Okay, so there is something deep that perhaps is shared by different symmetries. Okay? That was number one. Number two, I suggested the possibility of in this work thermodynamic scenario of showing how the imposition of a family symmetry can be consistent there, because there it must be consistent with Einstein's equation in the curved space. Okay? So we showed that this pattern can be consistent, and this is not a completely trivial thing, but it's also not so complicated. And concerning the origin of the mass hierarchy, it would have a geometrical meaning. So for mathematician, it can be a very attractive program. You have the hierarchies from geometry, and you have the mixings from symmetry, and the imposition of symmetry by itself can be completely consistent as it can be in the domain of four-dimensional theories. Moreover, in the same spirit of extra space-time dimension, we suggest that higher symmetry, for example, 6 space-time symmetry, may be able to completely reduce the ambiguity in this choice of the four-dimensional family symmetry. The family symmetry there would be a remnant of the isometries of the extra space, okay? And it will be completely, you have a unique symmetry in 4 dimensions. There is nothing you can do. Of course, I am being a little bit there is still some, to have a possibility of doing some model building. You may still, for example, impose a symmetry to stabilize your dark matter. That can be a discrete symmetry. We analyzed that with Antoniadis and company. So there is still the possibility, first of all, of reducing the symmetry to get the four-dimensional family symmetry as an emergent symmetry, but still there may be perhaps other symmetries to stabilize dark matter that you can kind of impose by hand or derive those symmetries from boundary conditions in the extra space. Okay? So there is a room there, but there is a room for model building. It's not a dead end. So this is, I think, still the symmetry idea is still, from my point of view, the best idea in model building to solve the family problem. And we are still far from the ultimate solution, but I don't think we are at the dead end. There are possibilities with tools that are open. Another tool which is popular now is this, I forgot the name. And we are also moving a little bit into that. You probably remember this.
Modular forms, do you mean?
Yeah, form, no. How are they called?
I don't know whether you're talking about modular forms or modular symmetries.
Exactly, modular symmetry. From I have something against modular symmetry, the fact that it comes associated with supersymmetry. And I myself did a lot of supersymmetric models, but at the moment, I must admit that we have not seen any hint of supersymmetry. We have not seen 𝗙𝗲 particles in colliders. We have not seen proton decays. However, maybe modular symmetry that could be a way 𝗙𝗲 could be manifest. So many of our constructions may be generalized to modular symmetry. And in fact, right now, I am looking at one of those possibilities. But I'm not preaching at the moment for modular symmetries, but they may open up possibilities that are not there and which may end up being mathematically rather attractive, maybe to a mathematically gifted person as our chairman. That may be also a possibility to go.
Okay, thank you. Is there another question in the audience here? Because I have a couple of more questions, but I don't know whether we can discuss it privately or let me just pose the next question. Basically, the title of your talk was really kind of suggestive. We want to know what comes next, and you showed us that there are several avenues in neutrino sector because there are experiments, etc. But of course, we are also willing to dream. And there is this dream about the 100TeV collider or accelerator, right?
Yes.
Do you think that there is something else? Let's suppose that it is built. We don't know. But if it is built, what do you imagine that's going to happen in there?
Well, it is difficult to be a prophet, you see.
Yes.
We got a Nobel Prize for high energy.
Let me say, what do you wish?
And it was meant, it was from experiments that were designed to measure proton decay. And what did they do? They inaugurated neutrino astronomy. They discovered neutrinos from the supernova.
Right.
And they discovered neutrino oscillations required to understand solar and atmospheric neutrinos. Neutrinos coming from the sky. Neither of these were the motivator of those experiments. Today we have the 𝗥𝗲𝘀𝗂𝗁𝗁. It has motivations perhaps associated to the theoretical issues, which are probably oversold concerning the naturalness and so on. But my driving message here was to say, neutrinos is a data-driven field, and these data-driven fields open us experimental, for example, possibilities for the future, and such as, for example, the 𝗥𝗲𝘀 or the IS. I'm giving you an example. Lepton flavor is conserved in nature as far as we can tell at the moment. And I'm telling you that these experiments may provide the discovery site of a new phenomenon, which people are now looking in a completely different territory. They are looking in mu-T-gamma, relatively low energy experiments, or in nuclear physics, mu-E conversion in nuclei. And maybe the answer is there. And this motivation is coming from neutrinos. We don't know at the moment the octants, the ordering of the neutrino spectrum. And perhaps it will take a long time for us to settle that. Maybe there is a small chance that the solution may come from a high energy experiment. This, insofar as experiment is concerned, but also theory. We don't know, we don't understand the strong CP problem. People think maybe it is due to the axiom and the 𝗥𝗀𝗀𝘁𝗂𝗁 symmetry. And one model that we did with our collaborators, including 𝗙𝗲𝗀𝗂𝗁𝗁, was to say that it came from this golden formula. In other words, the golden formula actually has a history. It came from an old paper of 𝗙𝗲𝗀𝗁 in which he had this formula, another piece of that equation that I showed of this equation, there was another piece, including the up-type fermion sector, including the top one. But that piece is totally wrong. So what we did in this paper was to show that to get rid of the wrong piece of his prediction, I needed the imposition of a 𝗙𝗂𝗀𝗃 symmetry. And that's why he became so happy that we wrote a couple of papers together. So this is probably a deep thing, the solution of the strong city problem. And it is motivated by neutrino physics, by the desire to understand the flavor problem in a neutrino setup.
Okay.
All I'm saying is that symmetry highlights the unity of physics, and neutrinos may play the leading role in the understanding of many of the drawbacks of the standard model. For example, another drawback is dark matter. Maybe dark matter owes its stability to the directness of the neutrinos. Maybe a profound connection, which completely changes our picture of the uniform. And neutrinos is the la voz cantante. I don't know how to say, is the leading theme in that connection, in opening our door to the future, enlightening our possible avenues for physics beyond the standard model. Maybe also the road to unification, maybe due to neutrinos.
Okay, fantastic. Very good. Thank you very much for these very interesting discussions. And this very interesting talk as well. I don't see any further question here in the audience, so I guess we have to stop here. But we have to thank you a lot for coming here, everybody else, and José Valle for accepting this nice invitation and giving us this talk. So see you then next time. We stop here. Thank you. Thank you.